Hi guys, welcome to our channel DSP NIT This is Malleshwari from EC department 3rd year. Today I am going to discuss about quantization errors in the direct computation of the DFT. Given a finite duration sequence x of n ranging from 0 less than or equal to small n less than or equal to capital N minus 1, the DFT of x of n is defined as capital X of k is equals to summation from n equal to 0 to n equal to capital N minus 1 x of n capital W from capital N to kn, where k equals to 0, 1, 2, 3 and so on n minus 1, where Wn is equals to e power minus j 2 pi by capital N. We assume that in general x of n is a complex valued sequence. We also assume that the real and imaginary components of x of n and Wn kn are represented by b bits. Consequently, the computation of the product x of n Wn kn requires 4 real multiplications. Each real multiplication is rounded from 2b bits to b bits, and hence there are 4 quantization errors for each complex valued multiplication. In the direct computation of the OFT, there are 10 complex valued multiplications for each point in the DFT. Therefore, the total number of real multiplications in the computation of a single point in the DFT is 4n. Consequently, there are 4n quantization errors. Let us evaluate the variance of the quantization errors in a fixed point computation of the DFT. First, we make the following assumptions about the statistical properties of the quantization errors. Those assumptions are: the quantization errors due to rounding are uniformly distributed random variables in the range minus delta by 2 to delta by 2, where delta is equals to 2 power minus b. The foreign quantization errors are mutually uncorrelated. The foreign quantization errors are uncorrelated with the sequence x of n. Since each of the quantization errors has a variance is equals to delta square by 12, that is also is equals to 2 power minus 2b by 12. The variance of the quantization errors from the 4n multiplication is equals to 4n psi e square, that is equals to n by 3 into 2 power minus 2b. Hence the variance of the quantization error is proportional to the size of DFT. Note that when n is a power of 2, the variance can be expressed as 2 power minus 2 into b minus v by 2 by 3. This expression implies that every fourfold increase in the size n of the DFT requires an additional bit in computational precision to offset the additional quantization errors. To prevent overflow, the input sequence to the DFT requires scaling. Clearly, an upper bound on mod of x of k is less than or equals to summation from small n equals to 0 to capital N minus 1 mod of x of n. If the dynamic range in addition is minus 1 to 1, then mod of x of k is less than 1 requires that summation from small n equal to 0 to capital N minus 1 mod of x of n less than 1. If mod of x of n is initially scaled such that mod of x of n is less than 1 for all n, then each point in the sequence can be divided by n to ensure that above statement is satisfied. The scaling implied by statement is extremely severe. For example, suppose that the signal sequence x of n is byte, and after scaling each value x of n of the sequence is uniformly distributed in the range minus 1 by n to 1 by n, then the variance of the signal sequence is equals to 2 by n whole square by 12, that is equals to 1 by 3 n square. And the variance of the output DFT coefficients mod of x of k is equals to capital N psi x square, that is equals to 1 by 3n. Thus, the signal to noise power ratio is psi x square by q psi q square, that is equals to 2 in 2 power 2b by n square. We observe that the scaling is responsible for reducing the SNR by n, and the combination of scaling and the quantization errors results in a total reduction that is proportional to n square. Hence, scaling the input sequence x of n to satisfy the statement imposes a severe penalty on the signal to noise ratio in the DFT. Thank you.